Hello everyone, I'm Arna Mitra. Today I would like to talk about 3D mensuration, which is essentially the study and calculation of surface area, lateral surface area, and volume of three-dimensional figures, such as a cube, sphere, cuboid, cone, cylinder, etc. With such a fundamental concept, it is used in every field. The formula of volume of a sphere 4 by 3 pi r cube is known to all of us, and we use it extensively. However, the origin of the formula is probably not known to all of us. Why are constants such as 4 by 3 or 1 by 3 there in the formula? To understand and answer these questions, it is necessary for us to understand integration first. Integration is the method used to add several small areas into a whole figure, such as sphere, cube, etc. It is the process of adding specific values of a function with respect to a change in a quantity to create a summation of an area over a range. It is a part of calculus. Integrals are also considered as antiderivative of a function. There are many representations of its formula. Three of those are shown here. This is the graphical representation of integration. The integral of a function fx is the area in the graph. As you can see, the area of the region ABCD in graph 1 is equivalent to the summation of area of smaller regions within ABCD as shown in graph 2. This is essentially the pictorial and simplified depiction of integration. So, with that understanding of integration, we will now derive the formula of the volume of the cone using integration. First, the cone will be cut into several horizontal discs. Each of the discs will have a very small height dx, such that every disc appears to be of the shape of a cylinder. Thus, the volume of the disk is equivalent to the volume of the cylinder, with height dx and radius r. Since these are two variables, uh, radius r and height from the base x, that would be changing in many of the disks in the cone, a relation has to be formed between variable r and x. Now, if we see the triangles AOB and ADC are similar right angle triangle, making the ratio of their similar sides equal. So capital R divided by capital H is equivalent to R divided by H. Also, from the triangle, small h can be replaced by capital H minus x. This provides a relation between r and x, and r becomes a function of x. On substituting r in the formula of volume of disk, x will be the only variable which will change from one disk to another. All other parameters such as capital R and capital H are fixed, as it is the radius and height of the cone which is constant. On integrating the value of volume of the disks, the volume of the cone is found. X will range from the minimum value of 0 to the maximum value capital H, which is the height of the cone. Therefore, these are the limits of integration, and formula in the yellow box. mm, mm, Integration from B to A, x raised to the power n dx is equal to x raised to the power n plus 1 divided by n plus 1 from B to A. Once the integration is complete, x is substituted by the values of the limits. Thus, we get the formula of the volume of the cone. The constant 1 by 3 arises from the formula of integration. Now that we have derived the volume of the cone, we will use the similar approach to derive the volume of a sphere. Again, we will derive the formula of the volume of the sphere using integration. For this derivation, a hemisphere will be taken into consideration. First, the hemisphere will be cut into several horizontal disks. Each of the disks will have a very small height dx, such that each disk appears to be of the shape of a cylinder. The volume of the disk is equivalent to the volume of the cylinder with height dx and radius r. Triangle COD is right angled. Therefore, on applying Pythagoras' theorem, a relation between r and x can be found. On substituting r in the formula of the volume of the disk, only x is the variable which will change from one disk to another. All other variables are constant. On integrating volume of disks, volume of hemisphere is found. X will range from minimum value 0 and maximum value r, radius of the sphere. These will be the limits of integration. The formula of integration will be used. Once the integration is complete, x will be substituted by the values of the limits. The formula of the volume of the hemisphere is found on solving it. It is known that the volume of the sphere is twice the volume of the hemisphere. Thus we get the formula of the volume of the sphere. The constant 4 by 3 therefore arises from the formula of integration. I hope you all have received an overview of 3D mensuration and answer to the question around the origin of the formula of volume of sphere and cone. I hope you found this video informative. Thank you.